Okay, I guess we'll start. Okay, so today we will continue with the hydrogen atom. First part of the lecture will be mathematical, just connecting it with spherical harmonics and Legendre polynomials. We actually solved the wave function, the spherical harmonics wave functions, but I would like to put it in a more general mathematical context. The second part will be solving the radial part, and hopefully we'll get to the third part and see what is the overall solution of the hydrogen wave function and the hydrogen spectrum. And probably that will continue to the next lecture. What does it mean about the periodic table? Amazingly, solving a problem with one neutron and one proton and one electron gives you enough information to reconstruct most of the properties of the periodic potential, which deals with atoms with tens and even hundreds of protons and electrons, which is in some sense very surprising. Okay, so we solve the eigen functions of the spherical part of the equation that depends on theta and phi, the angular momentum part. I would, and basically we have also written it down. And from the point of LL, we know how to use the ladder operators, creation and annihilation operators to go down to any LN. So basically we have the solution. I want to show you just that theta LM is basically the Legendre polynomial. Okay, to do that, I'll go back to the original equation where I'm already writing down the solution for phi, and I remain only with an equation on theta. So what I get there is so that's a differential equation. Looks quite ugly. And we will replace theta with x using the transformation Okay, we'll see if that helps us somehow to rewrite it in a simpler form. Okay, we have both cosines and sines here, and we have the theta, which we can write down. The usual game. So this immediately is dot to do x. And this we're ending up with writing an somewhat ugly expression, but it comes from sine squared plus cosine squared is equal to 1. Okay, so far so good. So we can just write down this equation in terms of x, and traditionally instead of theta we are writing f, but who cares? So we have now f is f of x. Okay, it's simple, just substitution of theta with x. For example, here I have this expression because sine squared is 1 minus cosine squared. So one here, one has to be a bit careful about writing down the terms, but in this case, for example, you have already here a sign that cancels out this sign, so it's immediately dot to do x. And instead of sine and multiplying it by this, you get 1 minus x squared. So far, so good. Okay. Now, for the case m equals 0, this is a well-known differential equation, goes back to the first part of the 19th century, end of the 18th century, where you had this whole school of French mathematicians that went and solved a lot of differential equations, and this is the Legendre. The Legendre equation. We don't have m anymore, it's equal to 0, so it's f of L in this case. X is equal to the Legendre polynomial, and the Legendre polynomial is just given by the following derivative. So, someone can tell me what is the value of it when L is equals 0?
One.
Correct. No derivative. Minus 1 to the power of 0 is 1. 2 to the power of 0 is 1. And 0 factorial is also 1. And so on and so forth, and I'm sure that if you Google, you'll find some site that gives you until that 1,000 or 10,000 polynomials. Okay, what can we say about these polynomials? Well, we know already from our previous experience, like with the Hermite polynomials, that we'll have orthogonality condition, recursive construction of a generating function. Okay, I'll just spell it out. First, orthogonality. Clearly, they are eigenfunctions. They have to fulfill orthogonality up to normalization, and here comes in the normalization. Why are these boundaries? Simply because if you remember that they come out of cosine theta, these are the boundaries. Again, it's an eigenfunction. The eigenfunction basis spans the whole Hilbert space. The Hilbert space in this case is defined only between -1 and 1, and any other function that is integrable, i.e. can be normalized, could be written as a sum of the eigenvectors.
can know that from Ström-Liouville, but then this means that the operator in this equation is Hermitian. So what does it measure?
Answer.
No, because in the beginning we that's just looking
Gives answer to the classic case.
the angular momentum, but in a different basis.
No, it's on a sector of the angular momentum. The sector of m equals 0.
So it's like
I tell you, well, you can measure a particle, but only between 0 and infinity. Still can define a measurement, an operator that goes between 0 and infinity. You define the operator x, but add the restriction x is larger than 0.
Okay.
Makes no sense, but you're allowed to do it. Here, because it's a particular sector of the Hilbert space, m equals 0, so measures the angular moment, the total angular momentum, but only for the m equals 0. What happens when m is not equal to 0? We'll add, I've erased already the eigenfunction.
D to the I m
Yeah.
phi.
And we'll have all of the Hilbert space.
Also, it's under the restriction that we have symmetry in phi.
It's under the restrictions that we are in the m equals 0 sector.
And that means symmetry in phi, right? Because otherwise you would depend on phi.
Yeah.
Okay, thanks.
Okay, generating function. Now, the point of giving all these properties, since we have found everything that we need to find already from the creation and annihilation, is mainly to give you some familiarity in the literature. So if someone says the solutions of the hydrogen atom are the Legendre polynomials, you know what they're talking about. And sometimes, like in the recursion relation that we'll have in a moment, it's sometimes easier to acquire it that way. Could be, instead of doing the derivative several times, perhaps going through a sequence of the polynomials might be easier. Okay, so the generating function. So that's a generating function. Someone can remind me what's a generating function? Yeah, what is it supposed to tell us? This is a generating function, but what does it tell us?
Maybe for different S it gets like a polynomial of the eigenfunction.
Yeah, but under what condition? A generating function is a function that if you take the S and take it in the limit of 0 and write down a Taylor expansion, you will get as the components of the Taylor expansion the polynomials that we are interested in. So basically, this is just as in any Taylor expansion, P. So it's another way to identify the Legendre polynomials or any polynomial depending on the generating function. And
shouldn't there be a plus before the square?
Yep. You see the plus and you don't remember what is a generating function.
I remember, like, can't rigorously define it.
Okay, and the recursion relation. Hopefully with the right pluses and minuses. But the basic thing, from the first two terms you can build all the Legendre polynomials. Okay, that's nice, but it's only for 1 second, 1 sector. So now the expansion for our case where we have it's not called the special, someone can check in Google what is the exact term for it. It's not the special Legendre. Yes, that's never used it in my life, so I can't remember what's the technical term, but again, you can check easily. Not surprising, but because we saw exactly the same structure out of the creation and annihilation operators. Okay, we have written it down. Now silently we can forget it. Now I move to a properties that has actually physical importance, and that, quite surprisingly, is the parity of the angular momentum. Why is that important? Because how do you measure the properties of the hydrogen atom? I'm asking the whole class. modern physics or high school physics or whatever. How do I
What do you
know?
mean by properties?
How do I know that the hydrogen atom has the spectrum that it's well known to have? Except for I checked it and that's what's written in the textbook or in Google. What do I measure actually?
Spectrum.
The spectrum. What spectrum?
You mean like photons coming out?
Exactly. We measure photons either being absorbed by this hydrogen atom or emitted from this hydrogen atom. We create the spectrum either by heating the hydrogen atom or by sending light, photons, into a gas of hydrogen atom and seeing what doesn't come out. That's absorption. So we measure photons. Now, what do photons have?
Energy.
Energy,
A moment.
momentum, and another property that is less discussed, at least on the elementary level.
I say spin.
I would say spin, but that's not correct. Not exactly correct. Because of the structure of the Maxwell equation, they have a strange property. Their spin is not the regular spin. You would think that photon is a spin 1 particle. Why spin 1? Well, it's a boson. I hope that much is not surprising. All force-carrying particles are bosons. Okay? So it has to have an integer spin. So either 0, 1, 2, it's not spin 0.
Oh.
How do you prove it? You go and buy a polarizing sunglasses. It has 2 polarization directions. So electromagnetic waves have 2 directions of polarization. Now we can say 2 doesn't work well with spin 1 particle. Why? Because spin 1 tells me n is 1, 0, minus 1, 3. What happened here? Because of the structure of the Maxwell's equation, you can't have a spin in the direction of k. So you lose. Always polarization is in 90 degrees to the direction
Okay.
of k. One of the most important and applicable and in some sense strange property of light. It's not usually when you're talking about a spin particle in an electron, who cares if it goes this way or that way? It can be spin up or down, doesn't matter the direction of k. In this case it matters. Anyhow, you have polarization. And if you have a definite polarization of light, it has a parity property, and therefore if you polarize your incoming or outgoing photons, you will see less transitions than could exist just because they don't conserve parity. The parity of the photon and the parity of the electron in the hydrogen atom have to be conserved with. So some transitions in spectroscopy are not allowed because of parity. But I said parity is conserved. Why? That we'll see.
Hey, can I ask you one question? You said like all force-carrying particles are bosons, but force does photons carry? Like, what do they carry?
The only force that lets you exist. Electromagnetic.
Alright.
Everything from the point, why does the electron rotate around the proton? Why do you have atoms?
That's the electromagnetic. Okay.
Till the structure of material, why don't all the atoms squish together but have some structure? To the fact that without electromagnetic forces you couldn't have spent 20 hours a day staring at a screen, because you won't get any information out of it. So basically...
So that's light that carrying that force? So that's light carrying that force?
Electromagnetic. Light is a specific
like
range of frequencies in this.
The photons, I mean.
Yeah. Almost everything that you see around you is electromagnetism, gravity. Now, gravity is so much weaker than the electromagnetic force. Let's say if I take you and put you in space, your atoms won't run away from each other, right?
Yeah.
So electromagnetism is much more important in keeping you together than gravity. So why is gravity important for the structure of the universe?
I mean, having galaxies?
Yeah, but why does it have this influence if it's so weak?
Because maybe we don't have repulsion, only...
Exactly, we have only one kind of gravity. So if we put together a lot of material, usually it will be electric neutral, but gravitationally not neutral. And the proposed particle that carries gravitation is a gravitino. Hasn't been seen experimentally due to the fact that the force is so weak. It's close to impossible to measure it directly, but if our quantum mechanical description of the world is correct, it has to be a particle with spin 2. Spin 2 is a boson. What other particles carrying force do you have? This is not within the material of the course, but it would be a shame if you graduate without knowing it. What are the two remaining forces?
The strong...
The strong electron is the strong force. And what does that do?
That's keeping the nuclei together, or the...
Right, they keep the nuclei together because it makes no sense. If I have 2 protons, 2 neutrons, the neutrons don't give a damn, but the protons would want to run away. They don't run away because of the strong nuclear force, and that's mediated by 3 bosons, W, Z plus, and Z minus, which are heavy particles, have mass, unlike electron and gravitons, which both are infinite. The force is 1 over r squared, which means just if you are constructing a shell around the source, it's just the number collected over the shell. meaning that they go to infinity. Nothing, the range of the force is infinite. These particles have mass, and the range falls off exponentially proportional to the mass, meaning the heavier they are. And that actually tells you why the natural occurrence of atoms ends somewhere around uranium. If you stop a minute to think why sticking together protons work up to 90 plus protons and fails further on, the simple range. The reason is that the force has finite range. Once you get to around 90, it's literally on the verge of breaking apart. That's nuclear fission. Just stick in another neutron or two, making it a bit bigger, the whole thing breaks up. And the remaining is a weak nuclear force. And what does that do?
Maybe molecules of two atoms? I'm not sure, I don't remember very well.
Radioactivity. It transforms a proton to a neutron plus a neutrino, or vice versa.
Wait, but that's only one decay. What about like the gamma and beta, I think you mean?
Well, that's a whole story of radioactivity, a science to itself, but what triggers it is a weak nuclear force. Actually, meaning that for most things that happen, it's not very important, but it's there. Actually, in modern physics terms, it's connected to the it has a similar structure to electromagnetism, and that's the electroweak unification. But, okay, that's a few years ahead in your education. But anyway, the important thing here is we see what happens in atoms by photons. So that's very important, let's say, in things like astrophysics. How do you know what is the composure of some star? Can't go there and pick up a scoop of material and check it. Just see the spectrum. Because photons come. Helium was first discovered on the sun, not on Earth. And how could they know that there is an atom that they don't know what, they have never seen it on Earth?
Wait, again?
In 1860, scientists came and said there's a type of atom that exists on the sun that doesn't exist here, and we are sure that it's there.
So they've never seen like the light spectrum of it?
No, that's exactly the point. They checked all the light spectrums on Earth, saw a new spectrum that doesn't fit anything else. Okay, from where it can come, must be a new atom, a new entry into the periodic table. Okay, so that's why parity is important. And the main claim here is that angular momentum has parity conservation, has a definite parity. Now, how will I prove it? We'll reach back to our old bag of tricks. Take out the parity operator. Show that it commutes with the angular momentum operator, and if it commutes, parity is conserved. As simple as that. Always, if I want to show that something is conserved, I show that it commutes with the Hamiltonian. Because what does it tell me? It tells me that there's no development in time. No development in time means that it's conserved. And I think I confused you. I said W and Z are the bosons carrying the weak force. For the strong force, what do we have? We have the gluons. There are 8 different particles. And they are a pain in the neck because what's special about, let's say, a photon? It is a particle connected to the electromagnetic force, but it doesn't carry charge.
Right.
Gravitons carry the charge of the strong force. So you have a field that is self-generating, pain in the neck, mathematically. That's quantum chromodynamics, things that isn't solved yet till the end. Okay, so back to parity. That's the definition of the parity operator. You might remember that we used this notation, operator pi, as the parity. Okay, unfortunately we Z, and in this case it's change plus to minus in each one. Nothing happens to R. Why? Because R is the normal of the radius. It's absolute value. I don't care in what direction, but it switches direction. So what we have is, instead of theta, we have pi minus theta. And instead of phi, we have phi plus pi. Okay. Phi becomes pi plus phi.
You have like, you can draw it.
Yeah, but I'm bad in drawing in 3 dimensions, but makes sense. So, Can just go, if you can't see it with drawing, just put in the definitions of theta and phi according to x, y, z, and see that that's what happens. Okay. Claims that this is true. Why? Well, if I'll go into in the polar coordination, it will be cumbersome. I have to exchange each theta for pi minus theta and each phi for phi plus pi and see what happens. Not terrible, but quite annoying. Here is one of the cases that this definition is easier. Why? We have a second derivative in x, y, z, meaning that if we have minus it's squared and we don't care about it. And we have a potential which depends only on x squared plus y squared plus z squared square root of everything. It depends only on r. Right? So it can't depend on plus or minus x, y, z. End of proof. Okay. So what is the conclusion? While M has a definite parity. Why? Because we can construct a set of eigenfunctions which are eigenfunctions of pi and h. Both of them and eigenfunctions of pi have a definite parity. So if I have a specific YLN, what is its parity? Let's see. Okay. I wrote it down explicitly. So here I'll get a plus and minus 1 depending on whether n is even or odd. Just because of this term. We have to see what happens with this guy when we exchange theta to pi minus theta. Remember, it was the Legendre polynomial of x, and x is cosine. So that's what I've written here. Elementary trigonometry. Why is that? Because the only place that I have cosine theta is in the derivative L minus N. The other parts are sines. Sines don't care about exchanging pi minus theta. And meaning that it's minus 1 plus and minus m. The parity of YLN is defined only by n. Okay, so we know now everything that we need to know about the theta and phi dependent part of the solution, which is actually the theta and phi part of any radial potential, meaning any potential which depends only on R. What is special about the hydrogen atom? The potential is the Coulomb potential, just electric attraction between the positive proton and the negative electron. So that's all we have. So now we have to put in a specific potential into the radial part of the equation, solve it, multiply it by the YLN, and we have the full solution of the hydrogen atom. Okay, now we have to refresh our memory, since the last time we touched the radial part was 3 or 4 weeks ago, before we went on this tour of angular momentum. And I don't know if you remember, but we got to a place where we wrote down a one-dimensional Schrödinger equation with special boundaries, and now we are going to solve it. What was special about the boundaries? Goes to infinity, but from 0, not to minus. Exactly. Just because R is defined between 0 and infinity. So R is defined between 0 and infinity. And we wrote down the Schrödinger equation. And we should recall that V effective is the Coulomb potential or any other potential you're interested in, plus the contribution of the angular part. If you don't remember from where it comes, this is actually also for classical Hamiltonians, it's not quantum mechanics. The only point of quantum mechanics is h bar L times L plus 1 instead of just L squared, the angular momentum in classical. Actually, this is the reason why we are not falling into the sun. Because if we didn't have angular momentum to begin with, there's no reason that the sun won't pull Earth to it because of this part. The fact that we have angular momentum and angular momentum is conserved counteracts the influence of V. And to remind us just, U was the radial part times R. We just use this substitution in order to write it in a simpler way. All of this we did about a month ago. Okay, now we have to solve it. Okay. From the point of view of a solution, what are the conditions in the solution? First of all, we have to be able to normalize the wave function, right? As in meaning that an integral from 0 and infinity of u squared dr 1 if you want. So, what do I conclude from it? First of all, right? Can't have a finite value of u infinitely far because the integral will diverge. I won't have normalization.
And 0 is not a singularity, right?
In a moment I'll talk about 0. Okay, I have to worry about 0. And the second part, if it's stronger than 1 over square root of r, it will diverge at 0. So I have to fulfill these conditions in order to have a solution. Yeah.
What about the Jacobian?
It's eaten into. You remember we developed it from the three-dimensional term. Here we are already in a one-dimensional equation, and the Jacobian is 1. Life is simple. Okay, this is again general for any form of V of R. Now I want to look a bit more carefully into the behavior of Coulomb-like potentials, or weak potentials. What do I mean by weak potentials? VR, when R goes to 0, is smaller than 1 over R squared.
Square root.
Not 1 over.
Oh, no.
It's a potential, it's not the wave function. Well, Coulomb potential definitely okay, 1 over R.
Yeah.
Why do I call it weak? Weak compared, when someone tells you something is weak, always the question, weak compared to what?
Okay.
So what do we know? Close to R equals 0, this guy gives me most of the contribution. So, as long as L is not equal 0 and we are talking about a weak potential, pay attention that this has to be fulfilled, because if it's equal 0, we have no contribution. So the weak part is the only part. So instead of solving the whole equation, I can write down at the area of r going to 0 okay, just writing down this equation without the dependence on v. This v gives me only a weak correction. So the solution can have one of two forms, either L plus 1, okay, first derivative L plus 1, and then times L, life's good, it's a solution. Or this solution is not good, I'm stuck with this part of the solution. Okay.
Why did you wrote that when r goes to infinity, you want that u goes to 0?
Because otherwise this integral will diverge.
Okay, so...
No normalization. But here I'm treating only the r equal to the vicinity of 0.
Okay.
Okay, now we'll look into the second part. L goes to infinity. Okay. In that limit, we don't care about this, because 1 over infinity is 0. I don't care about this. Physical intuition, very far from the Coulomb potential. I don't know if there is a Coulomb potential because its effect is 0, essentially. So I have only okay. This has two solutions depending on the value of E. Right? If E is positive, it's E to the power IKR. And if E is negative, it's e to the exponential of minus kappa r. Since we are interested here in down states, so E has to be smaller than 0. Above it, it's ionized. If you remember, that's already 2 months ago, if you have unbounded states, it's a continuum and behaves more or less like a free particle to some scattering. But at the moment, we're only interested in E smaller than 0. So the solution here is okay, so we have the two limits. Now all that's left, and that we'll do after the break. Combine. We know the behavior at r equals 0, in the vicinity of 0. We know the behavior at infinity, and we have to combine these two behaviors. Okay, we'll do it after the breaks. So we have the two limits of this function at 0 and at infinity. Let's propose a solution that extrapolates between those two limits and see what we will get. Okay, so first of all, just to make life a bit easier, instead of writing R, I'm writing a unitless variable. It's not H, it's K. Rho is K kappa times R, just to avoid units. Okay, and U of rho. Well, I need the behavior at small values of rho. I need the behavior at large values of rho. And I need some function extrapolating between those two limits, which will be W of rho. And now I'll have to find out what is W of rho. Okay, so I'll stick it in my equation for U. nothing more than explicitly writing instead of u, so expression performing the derivatives. A bit of work, but no tricks. The points that need some thought was to write it down with the correct limits. Okay, so I have an equation on W. Well, now, until now, I wasn't explicit about what is the form of the potential, except that it's weak potential. Okay, now, let's write down the Coulomb potential. Okay, what's Z here? Number of protons. Why do I write it in this way? We know that the number of protons in the hydrogen atom is simply 1. Because if I ionize an atom, meaning I get rid somehow of all the electrons except for 1, then I'm left with a Schrödinger equation for a single electron, things that I know how to treat. But I have Z times E positive charge. Z is the number of protons. Okay, so it's a meaning. And actually for the helium, they did a lot of experiments in the 20s and 30s to see what happens to an ionized helium spin, because it gives you some clue what is the importance of the strengths of the Coulomb interaction. Okay, so since we write down our equation in the dimensionless parameter rho, so I write also the potential in this dimensionless parameter. Okay, so I define the constant rho z. Good, so now I can rewrite everything that's written here. You see the reasons that I'm pulling out E, because here it's cancelled out. So I got some differential equation. Unfortunately, it's one of the differential equations that have a built-in solution. That's the Laguerre polynomial.
I haven't heard it.
You would be very insulted. Not to insult him twice. So, the solution is some polynomial, and we'll define it in a moment. But the most important thing, there is a solution only if the term here is integer. If not, there's no solution. What does it mean? We got quantization, as usual from the Schrödinger equation for bounded state. Not every energy can fulfill solution. Why do I call it energy? Because ρ0 is a function of energy. These are just constants. Kappa depends also on h bar. Okay. So we are used that the solutions of the hydrogen atom are written down in terms of small n, L and n. But here we have large n. So it's just a small redefinition. Let's write down n two. Okay, and actually here we have already the energy. Why? Let's not write down ρ0 squared. That's according to what's written there is 4n squared. But ρ0, if you remember from our previous definition, was just simply just I'm writing down the definition. No, Z is in the cup. I think that.
No, I think kappa is only in the Schrodinger equation.
Okay, right. It's not 2, it's Z. So. Okay, the minus dies out. If you're okay, I just wrote down the definition of Z, got rid of the minus because it's squared. Okay.
Times Z squared.
Times
Like
Z squared. And this is equal to 4n squared. So if I want to know what is the energy, okay, what does it mean? First of all, the energy doesn't depend on neither L or M. Depends on the number N. It's not that N doesn't depend on L. But what happens here is that L will set a limit on N. Why? Because the smallest value of large N is 0. So N cannot be larger than L plus 1. Smaller. So for L equals 0, I can have N equal 1. For L equal, for N equal 2, I can have L equal 1 at the most. So on and so forth. In a moment, we'll write it down exactly.
Oh, that's like the rings?
That's the rings.
Mm.
So the first thing is, depends only on N. N minimum is equal 1, because the lowest value of N that we can get here is large N equals 0 and L equals 0. We can't get anything lower than that. So this is the ground state. Higher values of N are higher and higher, because the negative value becomes smaller. When N goes to infinity, we have energy 0. So basically, if we look on the states in the potential, we have they become more and more dense until at E equals 0, they become a continuum. Approaching E equals 0, we are approaching the continuum. The distance between energies becomes. Okay. Now we get a hierarchy. We said if we have an N, L must be smaller than N. And M must be smaller or equal L. That we know out of the angular momentum part. So how do I fulfill all these conditions? Okay, let's create a table. N equal 1. L equals 0. No one other fulfills it. N equals 0, 1 state. So there's only one state in the ground state. N equal 2. L equal 0 and L equal 1. Both of them are possible. right? Both fulfill the condition of L smaller than n. 2 already doesn't fulfill it. If L is equal 0, n is equal 0. If L is equal 1, you have 4 states with the same energy. It's degenerate. Since the values of L and M don't influence the energy, I have 4 states in the second for the second energy. N equals 3, 0, 1, 2, a general N, or I could show it can convince yourself. So I have n squared degeneracy for each energy level. A lot of states once I'm moving higher up. Now, to make one thing that I forgot here is that electrons come with a spin. So in each state, I could have an electron with a plus, with an up and down. So if I take this into account, I have 2 times n squared degeneracy for each state. And this builds up the periodic table. Why is it? Periodic table is just filling up the number of electrons according to the states that are available. let's start doing the first couple of three periodic table states. Hydrogen. If you remember, it comes with 8 columns, right?
Yeah.
Okay, so 1, 2, 3, 4, 5, 6, 7, 8. A moment, try to explain why this structure. Okay. To make life complicated, this was invented, the periodic table was invented much before we had the solution to the Schrödinger equation, and the spectroscopic notation existed much before we knew this structure. So to make life complicated, instead of calling this state as it appears here, N1, L0, N0, it's usually the notation is 1s. 1 is like N, but the L equals 0 state receives the notation S. Actually, it continues even in physics and superconductivity. We talk about S states and in a moment, P states in a moment. You'll understand why. So, hydrogen has electrons in the 1s state. 1, n equal 1, L equals 0. They didn't care about this. We have only 2 states, 2 ground states that we can fill up here. So it's not amazing that we don't use all columns here. Helium. Two electrons in the 1s state. You can stop me and say, well, the 2 electrons have interactions between them, but the interactions are not strong enough to kick any one of them to a higher state. At this point, the separation between the first state and the second state is large. We saw that the spacing between levels becomes smaller and smaller as we go up, but for lower values it's still quite high. So interactions can't kick the electron to a higher state, so both of them, although they interact between themselves, are still well described by electrons sitting in the same state. Okay. Now comes an extremely important concept in chemistry. What is this called?
This column?
Mm-hmm.
Doesn't it like the
Noble gas.
yeah.
Why is it called noble? Because like any nobles, they don't like to interact with anything else. Rule of thumb, which can be proved, when a shell, and this is called a shell, is closed. What do I mean closed? It has full electron occupancy. The states are, the atom is happy, it doesn't want to do any chemistry. In a moment we'll explain what is chemistry. Okay. Next guy. Did someone open? I think it's lithium. Must be lithium.
Yeah.
Okay.
Sleep.
3 electrons, 2 1s. 2 are sitting in the ground state. Since we have a limited number of fermions per state, which is 1. The third has to go into the next state. 2 is understandable because it's n equal 2, but for some reason the sorry 2s and 2p. So I have 2s. What does it mean? It sits on n equal 2, L equal 0. There shouldn't be a difference in energy between these two cases, but small effects that we didn't take into account. Calculation breaks up a bit. All 8 atoms fill up that. Here I can put in 4 states, meaning we spin 8 electrons. Each one of them keeps a column up to, what is the guy here? Neon, right. And E, and this has 2 in 1s, 2 in 2s, 6 in 2p. A good periodic table gives you these fields.
Why there is 2 in 1s?
2 in 1s, 2 in the state, 2 in n equal 2, L equals 0. Six, because I have here 3 states times 2 in 2p. 2p n
Why it's times 2?
because of the spin. You can have up and down. I have 2 places to put everything.
Yes, that's what I thought.
Okay. Now let's do the first step in chemistry. What's the guy in the 7th?
Yeah.
What?
Fluoride.
Right, which will be 2 1s, 2 2s, and 5 2p. Okay? Now, the basic law of chemistry is that atoms that have filled shell are happy. Well, atoms that don't have filled shell want to lower their energy by exchanging electrons with other atoms. How can it be done? Okay. Lithium has 1 electron in its upper shell. 1 in an open shell. This guy is missing 1 electron in its open shell. So instead of leaving each one by itself, it creates a molecule. Just transfers 1 electron from here to fill up the shell, and he remains also with a filled shell. And since they are charged, they like to sit together. That's an ionic bond. Why ionic? Because it permanently gives 1 electron to the other atom, and they both are bound by electrostatics, living happily. These are salts. If you'll check the next or couple, just what is the next? Below lithium, what we have?
Sodium. Oh, sodium and chlorine. Yeah, that's salt.
That's a salt. It's exactly the same thing, because again, they just transfer. Guys in the middle, let's say, I think here it's carbon on the 4th or 5th. I think.
Yeah, on the. It's like. Yeah, on the 5th.
The 5th is carbon. Below it is germanium and silicon, right? Or
maybe it's
N.
Hmm?
Do you know? Well, I don't know what's called this. The signal is N, not C.
The N? What do you mean?
The gas, not the carbon.
No, on 5 it's carbon.
5 is carbon.
Maybe it's.
No,
I don't know. You want to watch? It's 6.
And so we have one. Alright, it's usually just F. Okay, let's use the correct notation. Here we have oxygen. Oh, you're right. This is nitrogen.
Also, yeah, it's 4. Sorry.
Carbon is 4.
4th, and we have here beryllium. Well, the point I want to make is, okay, let's look what's happening here. Oxygen. What does it miss? 2 electrons.
Yeah.
Oh, this guy, each one has 1. Let's combine with 2 of them.
What?
The stuff that you're drinking. H2O. And this is already 2 electrons makes it hard to have both electrons on the oxygen because it's too much Coulomb potential. So they start sharing it. They move it around. That's a covalent bond. While an ionic bond is permanent, covalents are all the time drifting around. The description is more complicated. That's why you have quantum chemistry, but the basic idea is fill up a shell that will create a molecule, and that's correct all the way down. Carbon, for example, carbon is in the worst situation. It's half-filled.
Oh, so it has like...
It has either to get rid of 4 or gain 4. Bad. You can't gain 4. It's too much. You have to somehow spread it around. That's why you create carbon change with hydrogens around it, with oxygens in it, all life, all organic molecules. Long chains of carbon. Why long chains? Because in a chain they can exchange 2, and then they have only 2 to worry about. Or they all share their 4 with all other carbons. Diamond, graphite, graphene, all these forms of carbon, they're very strongly bound because they really, really, really don't like to stand alone, because then it's the largest part missing or so basically Schrödinger equation explains us a lot of chemistry. Now what happens? We have another no. There we have again 8. Why 8? There should be here 3 to the power 2 times 2. Should have 18.
Oh, they jump one step, I think, and then
these
maybe 1D or something, 4D.
So this is known as 3Ds. L equal to is D. I don't remember even what is L3. Has also letters there. You see it doesn't go by any logical sequence here. But this is the 3S, this is the 3P. And here's you're already starting to break up all kinds of... So these 8 go together. 1 plus 3 times 2. These 8 remain more or less in the same energy and create a third. Then you have a strange occurrence. The 4S jumps before the 3D, and things start to become mixed up. More electrons, interaction is more important than the simple concept of just filling up the non-interacting hydrogen-like spectra becomes broken up. You can see that life becomes extremely bad for the rare earth. If you know something about all of the rare earths that we have, around 10 different elements there, fall on the same rubric of the periodic table. Why does that happen? Basically because they prefer to go to the S and P orbitals of a higher N, fill that first and fill the lower ones later, but the higher one determines the chemistry. So all their chemistry is very similar. So it's a very good description for the first couple of lines. Details become more and more important when you're going to higher and higher elements. But at the end of the day, the periodic table is built on these simple solutions of the Schrödinger equation for the hydrogen atom. If you stop for a minute and think about it, it's completely surprising. I solved a simple one proton, one electron equation and got more or less a reasonable guide for all atoms. There's exceptions and corrections and stuff once I get a real large number of electrons, but still quite good guide. Non-interacting, one electron, one proton, that's all. Surprising, very surprising, and basically something that immediately told people, well, quantum mechanics is useful. Even if we can't solve it with all details, we get a good intuitive picture of what happens in complicated systems. We get answers to why do we have types of molecules, ionic bonds and covalent bonds? Why carbon tends to build large structures while neon doesn't combine with anything, so on and so forth. So that's a great achievement of quantum mechanics and the relative simple solution of the hydrogen atom. What we will do in the next last meeting, basically we're missing two things. We still didn't write down the Leger polynomials. We just, from the simple structure of the solutions, N, L, and M, we learned a lot about the spectrum, but we haven't written down the full solution. And we should say something about scattering here. What do I mean? The case of E larger than 0. Okay, now the last hour I'll give you a material that is not included in the syllabus, not for the exam, but one of two, choose. I can do path integrals, explaining the way that Feynman looked on quantum mechanics, not through Schrödinger equation and so on, but integrals on path. One proposition, or do one of the few working quantum computing algorithms. What do you prefer?
Option 2.
Okay.
Let's see one more.
You are beaten in a democratic voting 2-1.
Democracy.
מה גורם לאלקטרונים לקפוץ, כאילו, לפורס מ-3D?
תראה, מה שקורה הוא שכשיש לי, נניח המצב הזה, ההפרש בין להוסיף 5 אלקטרונים פה ב-2P או 6 הוא קטן יחסית. לעומת זאת ההפרש של להוסיף מ-1s ל-2s הוא גדול יחסית. הרי אלו היו בעצם מנוונים, נכון?
כאילו משיקולי אנרגיה.
כן.
אני רוצה לעשות את זה.
אבל זה עולה לך אנרגיית אינטראקציה. אבל אם המטען שעובר הוא קטן יחסית, התוספת לאנרגיה הקולומבית היא יותר נמוכה מאשר הרווח באנרגיה הקוונטית, אז הם עושים את זה.
כאילו אני פה בערך מבין, לא עד זה. הבנתי. אבל בגדול זה כאילו עניין של שיקולי אנרגיה.
שיקולי אנרגיה, אין לנו.
נכון, לא להשפעה.
ברגע שהבנתי איך בנוי האנרגיות של אטום, אני מבין מהי האנרגיה הנמוכה ביותר.
מעניין אותי, אם לא תסבירו באמת על פס אינטגרל, מה זה בעצם הרגל אחת כזה?
על רגל אחת, במקום לעבוד עם הניוטוניאן, אתה עובד עם הלגרנג'יאן. ולגרנג'יאן אתה מכיר את עקרון הליסט אקשן. אינטגרל...
כאילו אני ראיתי את זה ביוטיוב וקראתי את זה טיפה, אבל לא היה לי לקחתי קורס בזה, או לא לקחתי אנליטי, מכניקה אנליטית, אז אני לא יודע ממש.
אז אתה צריך להבין מה זה לגרנג'יאן ומה זה עיקרון הליסט אקשן. וברגע שאתה מבין את זה, אתה מבין שבמקום שיהיה לך אינטגרל על... במקום לפתור משוואה דיפרנציאלית, אתה פותר מינימיזציה של אינטגרל מהסוג E בחזקת מינוס IS, שזה האקשן שקשור בלגרנג'יאן.
זה בשביל לפתור את האינטגרל הזה?
כן, והדברים האלו זה S של פס שונים, ואתה עושה אינטגרל על כל הפסס.
אינטגרל מסילתי?
כן. איך אתה...
זה נוח מתמטית?
לא. ולכן לא מלמדים את זה בסינגל פרטיקל, אבל לתורת שדות זה יותר נוח.
באמת?
כן. והסיבה הפשוטה, שאם אני אפתור שם הניוטוניאן, יהיו לי אינסופים כל זמן. פה אני יכול לשאול איזה פס יהיה מינימלי, אני לא נכנס לשיקולים של כלל האנרגיה בתוך
כי כאילו יש לך פה, כאילו...
אני יכול לבוא ולשאול שאלה ספציפית, התחלתי פה וגמרתי פה, מה הסיכוי לזה? בלי להיכנס לשאלות מה האנרגיה, כי שאלות מהסוג של מה האנרגיה, התשובה תהיה תמיד מתבדרת, זה לא יכול לענות על זה.
זה כאילו כמו הכללה של קולום בעצם, נגיד אם אני לוקח חשמל, אז קולום ואני לא הופך את זה נגיד למשוואת מקסוול עבור כאילו נגיד שדות וכזה, אז אותו כנ"ל?
נכון, אני עובר